Metal organic frameworks have the potential for application in a wide variety of mixture separations. Most commonly, the adsorption selectivity is used for evaluation and ranking of MOFs for any specific mixture separation application. The adsorption selectivity for a mixture of components 1 and 2 is defined as the ratio of the molar component loadings in the adsorbed phase, Q1 divided by Q2, divided by the mole fractions of components 1 and 2 in the feed gas mixture. Most commonly, the adsorption selectivity is determined from the ideal adsorbed solution theory. Now, mixture separations using MOFs are commonly carried out in fixed bed adsorbers, illustrated here for a specific example of the separation of ethine, component 1, and ethene, component 2. And a typical feed mixture would be 1% ethine, 99% ethene, and the objective in the separation is to produce purified ethene that is required as feedstocks for the polymerization reactor. The specification of the purity is typically that it should contain less than 40 ppm of ethine. In other words, for a feed mixture containing 1000 ppm ethine, we should ensure that the adsorbent MOF in the fixed bed is able to produce ethene with a purity corresponding to less than 40 ppm of the impurity ethine, C2H2. It is desirable to select a MOF that yields ethene of the required purity with the highest productivity. And the question arises whether the adsorption selectivity is the appropriate or indeed the only metric that governs the separation performance in a fixed bed adsorber. We address this question by using this mixture separation as an example. For further background on the variety of metrics used for evaluation of MOFs, I refer you to my publication in ACS Omega. See also my presentation on screening of MOFs on my YouTube channel. Before proceeding with the use of the IAST for the calculation of the various metrics that are used for screening and evaluation purposes, it is important to establish the accuracy and reliability of the IAST. As an example, we show here the unary isotherms for ethine and ethene in ZUL100. The continuous solid lines are the dual Langmuir-Freundlich fits. The data are for the unary isotherms are obtained using configurational bias Monte Carlo simulations of the unary isotherms and also for the mixture. The mixture adsorption equilibrium data are used to determine the selectivity of ethine to ethene for ZUL 100, shown by the green squares, and ZUL 200, shown by the red circles. The packing of ethine is more efficient within ZUL 100, and this results in a higher adsorption selectivity by a factor 4 in relation to the selectivity for ZUL 200. The CBMC simulations shown by the symbols are an excellent agreement with the IAST calculations with adsorption selectivity calculated from the corresponding unary isotherm data fits. Having established the accuracy and applicability of the IAST for describing ethine-ethene mixture adsorption equilibrium in ZUL 100, let us proceed to determine the metrics that describe mixture separations in a fixed bed adsorber. For this purpose, we consider the experimental data for ZUL 100, shown by the red circles, and the simplest description of breakthrough in a fixed bed adsorber is afforded by the shockwave model, wherein we assume that the concentration fronts of ethine and ethene traverse the length of the fixed bed in the form of shock waves. Further details of the shockwave model are available in these two publications. The use of the shockwave model helps us to determine the metrics that govern the separation performance in a fixed bed adsorber. Let's first start with the molar loading of component 1, Q1, which can be determined from the IAST. This, in the shockwave model for a fixed bed adsorber, is given by this expression, where Y10 is the mole fraction of component 1 at the inlet, Ct is the total molar concentration of the mixture at the pressure of 100 kilopascal and temperature of 298 Kelvin. Q naught is the flow rate of the gas mixture at the inlet. M adds is the mass of the absorbent. T1 is the breakthrough time. So if Q1 is calculated from the IAST, we can determine T1 from this expression where the experimental values for Q naught, M adds are used, and the T1 that is calculated is shown by the green line here. It is notable that the experimentally observed breakthroughs have a more distended characteristic than predicted by the shockwave model. We return to this topic in a few minutes. During this time interval, delta T, T1 minus T2, the delta T from the shockwave model can be calculated from IAST calculations of Q1, Q2 using this expression. The physical significance of delta Q2 is that it represents the amount of C2H4 ethene that is recovered during the time interval delta T. So delta T can be determined from the IAST calculations of delta Q2. We term this term delta Q2 as the separation potential, and it's the relevant metric for screening because it represents the maximum productivity of pure C2H4 that can be realized in a fixed bed adsorber, which the productivity in this time period delta T is represented by the green arrow, whereas in the breakthrough experiments, the actual productivity is lower than this value because of the distended nature of the breakthrough curves observed in the experiment. The departure from the shockwave model is primarily due to non-idealities in the gas flow within the tube, could be due to axial dispersion characteristics of the tube and or intracrystalline diffusion limitations. In any case, delta Q2 is the maximum realizable productivity, and this is calculable using the IAST. The adsorption selectivity is related to the delta time, delta T, determined from the shockwave model by this expression, and from the selectivity expression we can interrelate delta t, the time interval between the breakthroughs of component 2 and component 1, with the selectivity. Let's take a limiting case where the adsorption selectivity is unity. In other words, the adsorbent is non-selective. Then both components will break through at the same time, and delta t is 0, and that can be easily derived from this expression. So the shockwave model is useful to ascribe a physical significance to the adsorption selectivity as it relates to breakthroughs in a fixed bed adsorber. The closer the adsorption selectivity is to the value of unity, the shorter will be the distance between the breakthroughs of components 1 and 2. In the other limit of infinite adsorption selectivity, then the delta t is, can be derived as simply Y20 is the mole fraction of component 2 at the inlet times the breakthrough time for component 1. This essentially also means that as the selectivity increases in value, the separation distance between the two breakthroughs also increases, and that improves the productivity of component 2 that is required in purified form. So based on this analysis, we can conclude that besides the adsorption selectivity, an important metric that governs the separation performance for ethine-ethene separations is delta Q2, because it represents the maximum in the productivity of ethene that is realizable with a given MOF. To repeat again, delta Q2, Q1, and Q2 and S adsorption are all calculable from the IAST, but these interrelationships with the shockwave model allows us to focus in on the relevant metrics for a given separation. So if we are aiming for the highest productivity of C2H4, delta Q2 is the metric we should be looking at. For ethine-ethene separations, this graph plots the adsorption selectivity versus separation potential for 1, 2, 3, 4, 5, 6, 7 different MOFs. Interesting to note that UTSA 200 has a selectivity about 2 orders of magnitude higher than the other MOFs, but it does not have the highest separation potential. The highest separation potential, delta Q2, is obtained with the use of ZUL100. In order to confirm this hierarchy of productivities predicted by the IAST, let's return to the experimental data for ZUL100 and UTSA 200 for breakthroughs in a breakthrough tube. Indeed, we notice that the productivity values indicated by the blue arrows for UTSA 200 and the red arrow for ZUL 100 are indicative of the fact that ZUL 100 has a higher productivity so the hierarchy of delta Q2 values can be used for screening MOFs for this separation. In order to confirm this hierarchy, we proceed to the next step in our methodology by performing transient breakthrough simulations using a much more rigorous model than the shockwave model described earlier. In the transient breakthrough simulations, we take proper account of the intracrystalline diffusion as well as the fact that the concentration fronts in the actual adsorber will not traverse the column in the form of shock waves, but will have a more distended character that reflects the finite selectivity of adsorption with a given MOF.